So for the next several foils, we're going to talk about a topic that doesn't always get as much emphasis as it should, especially in most modern process technologies, and that's called crosstalk. And this is basically the fact that you have neighboring wires that have capacitance to each other. And keep in mind that a capacitor doesn't like to change its voltage instantaneously across the capacitor. So if you have, let's say, two neighboring wires, and let's say both of them are at a value of 1, and one of them switches from 1 to 0. Well, ideally you'd like that capacitance value to the actual capacitor between the two neighboring wires to switch from 1 to 0 instantaneously. But in reality, as the neighboring wire is switching from 1 to 0, that capacitance likes to keep the voltage delta between the two neighboring wires the same, because the voltage delta between the neighboring wires was 0 to begin with. They were both at a value of 1, and so there's no voltage difference between the two wires. So as the one wire is going from 1 to 0, the neighboring wire also wants to get pulled from 1 to 0. So in effect, that means that a wire that was supposed to stay at a constant value of 1 starts getting pulled down to 0. And this effect is called capacitive coupling or crosstalk. Sometimes it's called X-talk or noise, because the neighboring wire causes noise on the wire that wasn't supposed to switch, and that noise can be picked up by downstream logic that it's connected to. So the effects that you get due to crosstalk, the two main effects are, one is you'll get noise on wires that are supposed to be stable at a given time. Will get some noise on them, and that could induce noise to their downstream logic that's receiving this wire, that might cause that noise to be propagated down a logic cone and cause an incorrect value to be captured in a latch or a flop. Or if you cause noise on your clock wires, could make the clock appear like it's switching when it's not supposed to switch, and cause a latch or a flop to toggle and capture new data when it wasn't supposed to capture new data. So that can be very, very bad effects. The other thing that it can do is, if you have, let's say, a neighboring wire where one wire was supposed to switch from 1 to 0, and the neighboring wire was supposed to switch from 0 to 1, both at the same time, because they're capacitively coupling on each other, the effective capacitance looks like it's doubling, because the neighboring wire isn't stable. It's actually going in the opposite direction, and it will cause increased delay on wires that are next to each other that are switching in opposite directions. And so this increased delay needs to be modeled correctly, otherwise you'll get the wrong delay calculation, and you'll think that your circuit is faster than it is in reality. So crosstalk is very deceptive in some ways, and can be difficult to model and difficult to prepare for if you're not aware that it's happening. So here, let's go through and look at an example of how crosstalk can affect delay of a wire. So let's assume that we have two wires, A and B, routed next to each other. And here in the figure, the A and B are, again, going in and out of, they're perpendicular to the plane you're looking at. And so they're kind of going into the screen or out of the screen. And let's assume that all metal layers above and below the wires that we're talking about are quiet on average. They're not transitioning at all. And let's ignore the wires other than A and B that are next to it on either side. So we're kind of ignoring those for now. We're just looking at how A and B affect each other. So we can model our capacitance to ground. Let's say we take the C top, the capacitance to the layer above this, plus the capacitance to the layer below this. We're just modeling that as all being lumped to ground as C sub ground, and see how the overall capacitance is affected just by these two neighboring wires. And so the capacitance between wire A and B is C adjacent, and we'll see how C adjacent depends on the behavior of the neighbors. And this is what we're going to be measuring below is what's called the Miller effect or Miller coupling factor. So if we're looking at signal B and we say signal B is constant, and how does that affect signal A if signal A is switching? So if signal A switches, the delta in voltage between A and B, between if it's switching between 0 and VDD, it's a delta of VDD. Because whatever B was stayed constant, A is switching between 0 and VDD, so you have a delta V of VDD. The effective capacitance that's seen is C ground plus C adjacent, because you're going to be switching the full VDD delta between those two that are both staying constant, and the effective Miller coupling factor is just 1 because you count the entire effective capacitance C adjacent. Now let's say if B is switching in the same direction as A and they're both switching at the same time. In this case, B and A don't have any delta voltage between them. They started at the same voltage, either 0 or 1, and they're ending at the same voltage, either 1 or 0. And so if they're both switching at the same time, they started at the same voltage, ending at the same voltage. There's no delta in voltage as they switch. So the only delta in voltage we see is between the signals and ground. So we only the effective capacitance is C ground, and the Miller coupling factor that we would multiply C adjacent by is a factor of 0. So effectively C adjacent gets zeroed out, and that so it causes us to switch faster if we have two neighboring wires switching in the same direction. Now if the two neighboring wires are switching in the opposite direction, then we see a delta V of 2 VDD. So if A started at 0 and B started at 1, and they're switching in the opposite direction, we now see one of them is trying to go up by 1 volt, the other one's trying to go down by 1 volt. So there's a 2 volt difference in the voltage across the capacitor C adjacent. So this gets seen as an effective resistance of 2 times C adjacent. And so we have to, for our effective capacitance calculation, we have to multiply that C adjacent by a factor of 2, which is the Miller coupling factor, multiplication factor, and will cause the signal to be a lot slower, switching in opposite directions to neighboring signals. And so you can see where, depending on what values of signals are next to each other and which direction they're switching both at the same time, they could either help each other or hurt each other, and your max delay and min delay will have a large variation on it depending on which direction the signals are toggling. And so you have to calculate max delay based on an MCF of 2, and you have to calculate your min delay based on an MCF of 0. And that has to go into your timing tool and timing modeling, which makes your timing definitely more difficult to meet both max delay and min delay when you have these effects along with other effects that make your max and min delay have vastly different times as well. So I just went through how crosstalk affects delay. Now I'm going to talk about how crosstalk affects noise. There's two different possible ways that crosstalk noise happens. One is crosstalk can happen on and cause noise. Crosstalk, like I said before, noise, the time that it matters to us is on a wire that's not switching. So delay matters when two wires are switching at the same time. Noise matters when one wire was supposed to not be switching and the other one was switching. So one possible way that your wire is not switching is if the victim wire, so the terminology used here is the wire that's switching is called the aggressor wire or the attacker, and the wire that's not switching is called the victim wire. And so if the victim wire is floating, so it doesn't have any active driver on it, that just means the victim only has capacitance on it. And so in this case, you can model the victim wire as a capacitive voltage divider. And so you have to take the capacitance between the aggressor and victim as the C adjacent and divide that by the C ground of the victim wire plus C adjacent, and the amount that the victim wire is going to change is going to be a capacitive voltage divider times the delta of what the amount of voltage that your aggressor is changing by. So that's a fairly standard thing that we do in RC circuits all the time, is a capacitive voltage divider. So while we talked about having a aggressor on a victim where there is no driver on that victim in the previous foil, in reality, if you have a wire that has no active driver on it, typically that's not a wire that you care if there's any aggressor on it. Usually if you have a wire that you want to be a given value, there's always a driver on it. So usually your victims, the victims that you care about are ones that actually have an active driver on them that is trying to fight the noise that is being induced by the aggressor. So in this case, your noise is going to depend on the relative resistances of your aggressor driver versus your victim driver, as well as the ratio of capacitance of your C adjacent to C ground of the victim. So below there's some equations for what change in voltage you might expect on a victim where it wants to stay stable, but it will have an induced voltage noise on it. That's a ratio of C adjacent to C ground plus C adjacent times a factor that's related to the aggressor strength versus the victim strength that's trying to keep the victim wire stable. And one thing to keep in mind is your victim driver, if it's like, for example, you have a victim wire that's trying to stay at ground, and so it's pulled its victim wire down to ground and it's staying at ground. That means that that transistor, an NMOS transistor pulling down to ground, is deeply into the linear region. The VDS across that transistor is close to 0. You've pulled the wire pretty close to ground already. So the linear region has a certain resistance to it, whereas your attacker is in the process of switching, so it's still in the saturation region. So the regions that you're in, if the size of your aggressor trying to switch the aggressor from 0 to 1 is approximately the same size as your victim, because you're in different operating regions for those transistors, the resistance of your aggressor is going to be about 2 to 4x the resistance of the victim. So that goes into your equation as well. I'm not going to go through actually calculating a delta victim or delta voltage in your victim because in reality it's usually a lot better to try and do a simulation to figure this out than hand calculations anyway. These calculations can get very, very complex. So, but we'll let's go through just a couple of examples, or just an idea of how much voltage delta you can get in a victim with respect to driver and receiver sizes, or aggressor and victim sizes of drivers in the next foil. So in this foil you can see we have some simulations where we've simulated the coupling or the amount of delta voltage that you'll see for a victim if you have an aggressor switching from 0 to 1 and a victim trying to stay at a value of 1 for some different situations. If we assume that the C adjacent is equal to the C ground for a victim, what type of noise would you expect to see on different types of wires? So for the aggressor, it's going between, again, starting at a value of 0 and ramping up to a value of 1. The first dashed wire you see there is if we have a victim that is undriven, so it has nothing trying to fight that aggressor. If, again, C adjacent is equal to C ground, you will get half of the voltage of the aggressor onto the victim. Because C adjacent equal to C ground, the capacitive voltage divider, you get half of that voltage. Now, if C adjacent is equal to C ground, but we have a driver trying to fight that, and the victim driver, let's say, is even only half the size of the driver wire, that next dash line shows that you get about a peak voltage on the victim of maybe just a little bit less than 0.2 volts. So you can see that having a victim driver to fight the aggressor definitely helps to reduce the amount of voltage delta on the victim. And then when we get to a victim driver that's equal in size to the aggressor wire, aggressor driver, we get maybe only a peak of 0.1 volts, so only 10% of your total aggressor voltage is actually seen as a peak voltage on the victim. And then, of course, going to a victim of double the size, you see even half that voltage, so maybe only 0.05 volts. So it definitely helps to have a larger victim driver than the aggressor driver, but keep in mind this noise can have somewhat of an additive effect if we have multiple wires. So let's say you have a wire on either side of a given victim and both of those wires are going at the same time. We could see a doubling of this voltage value potentially. So you can see there could be occasions where you have a really strong aggressor and maybe a really weak victim and have multiple attackers on either side and possibly even attackers above and below in the wires, wire layers, one layer above and one layer below, that could all cause potential noise on a given victim and cause a potentially significant amount of noise depending on the situation. So I've definitely seen times where you could have a wire have a huge amount of noise on it but you have so many tens of thousands of wires that even if you only have one out of 10,000, that could be the one that causes your overall device or integrated circuit chip to fail. Now you might ask, so what if we have noise? What's the big deal? So let's go through the implications of if you have noise on a wire. Now, first of all, if the noise is less than the noise margin of any receiving gates, such that, yeah, you could have a rise of 0.2 volts on a given input to a gate, but that 0.2 volts won't cause the output of that gate to switch. Basically nothing happens. It's really not a big deal, and we can tolerate that amount of noise. Now, we could also, in static CMOS logic, if we have noise and then that noise gets overridden by the victim driver, it will eventually settle back into a correct output, even if you have a large noise spike that does cause a glitch. But keep in mind that if you have a glitch that can propagate through the receiver stage, it will in effect either cause extra delay or it will cause a switch at a time when your timing tools aren't actually searching for a change in the value of the signal. And so it could cause something to switch at a time when it actually will get captured in a downstream latch or flop as an incorrect value. So that's the most problematic. A slightly less problematic thing is the glitching that you get from these false transitions could cause some extra power. Usually that's probably a second order effect that's not too concerning. But in static logic, that's probably the main problem is the glitch could happen at a time where if it's just at exactly the time when a downstream flop is trying to capture that delay, as that glitch comes in, you get an incorrect value. More problematic, or more likely to be problematic, is if you're using dynamic logic. Dynamic logic, if it gets a glitch on it, it never recovers from the glitch because it's kind of a one-shot thing. As soon as it switches, it stays in that new state until you get a pre-charge value to come in and reset the dynamic logic. So dynamic logic, you have to be very, very, very careful with noise. It's very sensitive, and so that's one of the things that makes dynamic logic quite hard to do. And then also, if you have memories, memory structures, and there's other sensitive circuits. If you get a glitch on them, it can flip the value of the memory and cause you to capture an incorrect value that could stay there for a while. And one thing that I'll make a note of that's not on this slide is the really difficult thing about noise is if you do have a noise glitch that causes a real problem, it tends to be very hard to debug because it's very dependent on specific signals, the order in which wires are switching over time, and it's really it's not necessarily repeatable in a way that other failures are repeatable. And so it can be very difficult to debug and cost you a lot of time and effort to actually find the problem and fix it if you actually generate this type of problem on real silicon. So let's go into some factors that might go into how you engineer your wires. So as I mentioned, the delay effects, the RC delay, the noise problems of your wires means you can't just ignore and go out and route your wires however you want to in all cases. In some cases that might be possible and might not cause any problems, but in a lot of cases you actually have to pay attention to your wires as much as you pay attention to your logic gates and your transistor sizes, etc. So your goal is to achieve a small delay as possible in areas where your delay is most critical, to have as little area consumption as possible, and meet your power goals with an acceptable amount of noise, meaning less noise than actually causes a problem. So the degrees of freedom that you have are the width and spacing of your wires. Two things to keep in mind is, from one standpoint, the wider wire that you have as possible, the lower resistance you have. And the more spacing you have between your wires, the lower capacitance you have. But if you use all wide wires with wide spacing, you get very few wires that, and you might get a lot less number of wires than you need in order to wire up your design. The other thing to keep in mind is while a wider wire is good from a lower resistance standpoint, the wider wire will have more capacitance to the layer above it and the layer below it. And so not always is a wider wire a lower total delay. Depending on how long your wire is and how big a driver you have on your wire and how much load you have at the end of your wire, all of those go into it. You might find that a narrower wire gives you less total delay than a wider wire in certain cases. So there's lots of factors to look at. So here's just some examples of different wire pitch and what that does as far as the coupling to spacing wire, neighboring wires, what that has as to, in terms of what the RC delay is of the wires. So all of these factors go into trying to decide what width and spacing. Then of course the metal layer that you're using, higher metal layers tend to have lower resistance and the capacitance might be approximately the same, but because the higher layers have taller wires, it's not always the case that a higher metal layer has less capacitance. It all depends on exactly how much the spacing between your wires is, because the thickness is definitely higher. So overall you could have a higher capacitance if you have the space is equal to a lower metal layer. Shielding can definitely help. So rather than putting two switching wires right next to each other, you can put a wire next to the track next to either VCC or ground, and you'll now have a constant voltage next to it, so you won't have any coupling going in the opposite direction when you're trying to switch. So shielding can help prevent or reduce your noise. Down below here we can see an example of how shielding can be used. So in the lower left we can see some tracks where we have VDD and then A0, A1, and then a ground wire, and then A2, A3. So each of the A wires is always next to a constant, either VDD or ground, and only next to one neighboring wire that can switch. So this is called half shielded, where one side is a shield and the other side is a potentially switching wire. This gives you a reasonable number of routing tracks, but also a reasonable number of reasonably well shielded for noise. The middle set of tracks shows where every other wire is a signal track and every other one is either VDD or ground. So we have VDD and then A0, then ground, then A1, and then VDD again. So in this case, this is what's called full shielding. The problem is with this, you get many fewer signal tracks because you're taking every other track for a power or ground track. But it does give you the most most noise insensitive design. So it's very good for noise, but it does drastically reduce the number of total tracks that you have available for routing real signals. So you can't use this in most of the areas of your design because you'll generally need more signal tracks than just every other track of your design. And then finally on the right hand side we're showing where you might be able to you have no power tracks, all the signal tracks. This is potentially the most noise problematic, but if you have some knowledge of your signals, you can use what's called logical shielding. For example, if you know the signals A and signals B never switch at the same time as each other. And so A is always going to be stable when B is switching, and vice versa. This will help as far as timing goes, because you know that your A signal, when it switches, is never going to be slowed down by B trying to switch in the opposite direction. But it doesn't necessarily help as far as noise goes, because both A0 and A1 can both switch in the same direction and be attackers on B0 at the same time. So logical shielding can sometimes help for one type of noise effect, like the Miller coupling effect and delay, causing extra delay effect, but they might hurt for other types of effects like noise effects, as I just talked about. So the last thing that I want to talk about with respect to wires is RC delay and how repeaters are used in order to help improve your RC delay of your wires. So keep in mind that your value of resistance and value of capacitance are each proportional to the L, or length of your wire. This means that when you do the RC time constant delay, or RC product delay of the wire itself, is going to be proportional to the square of L. So each R and C are proportional to L. You multiply them together and you get L squared. So if you have really long wires, this factor of L squared causes your delay to be unacceptably large for long wires. With this in mind, typically what we try to do is break really long wires into shorter segments, so n number of shorter segments, with each segment being driven by either an inverter or a buffer, depending on, there's a few different reasons why you might want to use inverters. Sometimes inverters can be a little bit faster, but you have to keep track of whether you have an inverted version of the signal or a non-inverted version at any point when you're trying to tap off of the signal as you're routing it around. Whereas if you use buffers, you know the polarity of the signal is always the same with each wire segment. So there's some pros and cons there to be aware of. And so here's just depicting how we might have a really long wire segment between a driver and a receiver, and if it's incredibly long, you might be able to improve the delay of getting the signal from the driver to the receiver by breaking it up into n number of smaller segments. So let's go through a short, relatively easy example for doing repeaters on a long RC wire. So let's assume that we have a wire length of L and a RC delay from the driver to the receiver of 200 picoseconds. And now we want to add a repeater buffer in the middle of that wire, so halfway in the middle, between the driver and receiver, and that buffer we'll assume has a delay through the buffer of 20 picoseconds. So what is our new total delay? So let's do this as kind of a short quiz here. Go ahead and pause and try to figure this out, and then restart playing once you've got your solution. So let's go through and solve this. So the first thing we do is we're putting a buffer in the middle of the existing wire of L. So we now have two wires, one on either side of this new buffer, and each of those wires has a new length of L divided by 2, because we have our buffer right in the very center of the previous wire. So now having two wires that are each a length of L over 2, this gives us a new resistance value, which is R over 2, and a new capacitance value, which is C over 2. And this means we have a new RC value for each of these wires, which is R new times C new is going to be an RC of the previous RC value divided by 4, which the previous RC value of our original wire was 200 picoseconds. So now our new RC value is 50 picoseconds. So we now have 2 wires on either side of the buffer that have a delay of 50 picoseconds. And our new total delay is going to be 50 picoseconds for each of the wires, plus the 20 picoseconds for the delay of the new buffer that we added. And so we get 50 plus 50 plus 20 is 120 picoseconds from the driver to receiver. And that compares to our previous delay of 200 picoseconds. And the new delay is a factor of 0.6 of the original delay. So while we've added an additional stage delay into our overall circuit, we've decreased the overall delay by 40%. So this is a really good way to get better delays out of your circuit, even though you're adding additional stages to your circuit. So keep in mind, when you get long metal wires, adding repeaters in them can actually help improve your overall timing. So the example that we just went through shows how repeaters can actually reduce the amount of total delay in, especially for long wires that you have to go a long distance to get to a receiver. The question is, there's several questions related to this. If we want to optimize your delay as much as possible, one question is, how many repeaters should you actually use? How large should each repeater be? So we can basically build some equivalent circuits in order to try and answer those questions. So below we can see a potential equivalent circuit drawn for a repeater. Here we have a wire length of L divided by N, where N is the number of repeaters you have. This means your wire capacitance will be your capacitance per unit width times L divided by N. Your resistance of your wire is going to be your resistance per unit width times L divided by N. And then, of course, you can model in your inverter width is going to be your NMOS width, and your PMOS two times the width of that if you have a normal sized inverter. And you also need to model your gate capacitance, which is going to be gate capacitance C prime times whatever width you have, and the resistance of that effective resistance of your transistor is R divided by W. The larger width that you have, the lower resistance you'll have modeled for your transistor. And you can use this type of analysis to try and go in and figure out what the ideal number of stages is and the ideal size of your inverter should be. Now, based on the setup that we gave in the previous foil, we can start writing some equations for Elmore delay and try to differentiate with respect to the width of your transistor and n number of stages, and try to set this all equal to 0 in order, once we do the differentiation, similar to what we did for number of logical stages, if we differentiate and in order to set the equation to 0, you can find a local minima in order to find the ideal timing. I'm not going to go through these equations in detail. If you want to see this actually described in more detail, it takes a lot of explanation to go through. This is gone through in the book in chapter 6, at least in the version 4 release, 4th edition release It's in the neighborhood of pages 230 through 232. So I recommend, if you care enough about how this derivation goes, to go through the derivation there. But generally, I've never gone through the equations to try and find the ideal number of repeaters for a given distance. Generally, what we wind up doing at Intel is trying to, for a new process technology, you can do simulations and vary the amount of distance. You'll generally have a certain repeater size that you find out is ideal for, depending on what metal layers you're trying to drive your repeater across. And then you can do some simulations where you vary the amount of distance and find an ideal distance that you drive based on the metal layer that you're in and the repeater size that you're using. And then you just place a repeater every X amount of distance that you determine as your ideal distance. And so generally I don't ever use the equations to try and figure out an ideal number of repeaters for a given distance, but try to figure out the ideal distance between repeaters for a given process technology and metal layer. So one final thing to note about repeaters is the previous discussion was how to minimize the delay getting from a driver to a receiver that's a long distance away. And so putting in repeaters will improve your delay for long distances, but it will also increase your total amount of power consumed because each repeater will add some additional amount of gate size and additional amount of power to an energy required. So if you add really large repeaters in order to try and minimize your delay, it could add extra power to your design. And so sometimes you might want to balance your power versus your delay and put in smaller repeaters than would guarantee you the minimum delay in order to reduce the additional power that gets added to the design. So just the comment here is saying if you actually put in the optimal size repeater transistors or repeater inverters or buffers, you could get an 87% premium of power over just the regular wire being there, and you can reduce that additional power consumption, reduce how much that increase is. Instead of being 80%, maybe down to just 30%, or even down to 15% or so, by not going to the absolute minimum delay, but by using a non-optimal delay but lower power solution. And so most of the time that type of trade-off is done in industry. You don't necessarily always want the absolute minimum delay, but you're balancing delay with power consumption on a continual basis.